In this video, we are going to discuss the modified Euler's method, which is a numerical method to obtain the numerical solution of the initial value problems containing first order ordinary differential equations. This method is just an improvement of Euler's method. So let's discuss what is modified Euler's method. So here the problem is to find y at x equal to alpha from this initial value problem, dy by dx equal to fxy, where y at x0 equal to y0. To find y at x equal to alpha, the idea is to divide the interval x0 to alpha into n equal parts of size h by taking the points x0, x1 up to xn, where xn equal to alpha. Now suppose y equal to yx be the solution curve, where this yx is not known at this point of time. What is known at this point of time is the slope at any point to this curve and the initial point x0, y0. So using this information, we have to obtain y at x equal to alpha. So for this purpose, we divide the interval into n equal parts. And if you look at the graph, we see that this curve is not known at this point of time, but we can draw the tangent at x0, y0. So if we draw the tangent at x0, y0, then this is the equation of the tangent, y minus y0 equal to dy by dx at x0, y0 into x minus x0, where this f of x0, y0 is the slope dy by dx at x0, y0, and from this tangent we can estimate y1 as y0 plus h into f of x0, y0. This is the estimate of y1 we obtained in Euler's method, and this y1 is the point of intersection of this line, vertical line x1, and this tangent. So this is the estimate of y1. So this is the estimate of y1 we obtained using Euler's method. But we see that this is the estimate of y1 and this is the actual y1. So actual y1 will be here corresponding to this point on this curve. So we see that there is an error in this y1. So if we obtain y1 using Euler's method, we see that the error is large. This error can be reduced by replacing this tangent by another line of the slope as the average of the slopes at x0, y0 and x1, y1. So this is the new line with the slope f of x0 plus y0 plus f of x1, y1 by 2. So this yellow line is the new line. Instead of taking this tangent, we take this line. The estimate of y1 from this line is the point of intersection of x1 with this line. So this is the new estimate of y1, and we see that this is better approximation to y1 as compared to that y1 we obtain in Euler's method. So here error is reduced. So this is the idea. At each point x0, y0, x1, y1 up to xn minus 1, yn minus 1, we replace the tangent by another line with the slope as the average of the slopes at two consecutive points, and find the estimate of y using the point of intersection of this line with that vertical line. So in this way, we obtain better values of y1, y2 up to yn. This is the idea of modified Euler's method. So if we derive this modified Euler's method, then we start from the tangent at x0, y0. So tangent at x0, y0 is this. From here we get estimate of y1. This y1 is the estimate we obtained in Euler's method. So this is by Euler's method. For better approximation to y1, we replace this tangent by another line with the slope equal to average of the slope at x0, y0 and x1, y1. So the better approximation to y1 is given by this line, y minus y0. This is y minus y0 equal to average of the slopes at x0, y0 and x1, y1 into x minus x0. From here we get better approximation to y1 as y0 plus h by 2 f of x0, y0 plus f of x1, y1. Now this y1 is obtained by Euler's method. So we have already obtained this y1 0 by Euler's method. So we use this y1 0 in this formula to obtain better approximation of y1. Repeat the process until we get y1k minus 1 equal to y1k. So we stop here and we find that the approximation to y1 is now this. So this is the better value of y1 as compared to that we obtained in Euler's method. Now starting from x1, y1, again repeating the same argument, we find y2 0 using Euler's method, and then better approximation to y2 are given by the line with the slope equal to again average of the slopes at x1, y1 and x2, y2. Now this y2 0 is used in this y2. So this y2 0 is obtained from the Euler's method. So repeating this process, we find the better approximation to y2, and in finite number of steps we find that these two y2s are equal, y2p minus 1 equal to y2p. So if we find these two y2 are equal, then this is the estimate of y2. So we repeat this process for another points y3, y4 up to yn minus 1, And we find that in general the modified Euler's method is given by these two formulae. So a modified Euler's method is the combination of these two formulae. So at each step we have to use these two formulae to find the better approximations to y1, y2 up to yn. So let's take an example. Find y at 2.25 using modified Euler's method in 3 steps from this initial value problem. From here we note down f of xy is minus x plus y cos x upon 1 plus sin x, which is this. x0 is 1.5, y0 is 3.25. So starting with these informations, so we have to find in 3 steps. So we divide this interval 1.5 to 2.25 in 3 steps. So we divide this interval into 3 steps by taking h 2.25 minus 1.5 by 3, which is 0.25. So now we have 3 points, x0 equal to 1.5, x1 equal to 1.75, x2 equal to 2, and x3 equal to 2.25. So here at x0 we have y0 equal to 3.25, but at other points x1, x2, x3 we have to find y1, y2, y3 using modified Euler's method. So first of all we apply Euler's method to find y1. So this is now applying modified Euler's method. Now at step 1 we take x0 equal to 1.5, y0 equal to 3.25, and we find an initial approximation to y1 using Euler's method. So this is by Euler's method. So this is y1, which is 3.0335. So this is an estimate of y1 using Euler's method. Now we apply the second formula and find better approximations to y1. For this we derive the formula for y1. So y1k is this, f of x0, y0 is this, and h is 0.25, y0 is 3.25. Here x1 is 1.75 and y1k minus 1 is as it is. Now this value is constant throughout the calculation. So we calculate this value, and this value is found to be 3.1417, and this is 0.125 into f of 1.75 y1 k minus 1. So this is the formula for the better approximations to y1. Now use this y1. So y11 is 3.1417 plus 0.125 into f of 1.75 y10. Y10 is obtained using Euler's method. So if we calculate this, we find that this is equal to 3.0655. So this is better approximation to y1 as compared to y1 obtained in Euler's method. Then using the same formula again for y12, this is next better approximation to y1. So here the change is the value of y1. So here we use y11 and keep all other values as they are. So here y11 is 3.0655. So we replace this y11, we replace this y10 by y11. So in this formula we replace this 3.0335 with 3.0655 and solve. So if we solve it, we get 3.0659, which is again next better approximation to y1 as compared to 3.0655. Again using the same formula we get next better approximation to y1. So this is the formula. Here we replace y11 by y12. So y12 is 3.0659. So we put 3.0659 here. So using the same formula again and again, we find that y13 is 3.0659. So these two values are the same. Therefore, we take the estimation of y1 as 3.0659 because these two values are repeating. So now we have x1 equal to 1.75 and y1 equal to 3.0659. Now we start from x1 y1 and repeat this procedure again. So starting with x1 y1, we find an estimate of y2 by using Euler's method. So this is the estimate of y2 by Euler's method, which is 2.9142. Now better approximation to this y2 is given by modified Euler's formula. So here this is the better approximation to y2. Again this value will remain constant throughout the calculation. So we calculate this. So this value is found to be 2.9901 and this is 0.125 into f of 2 y2 k minus 1. So using various values of k, you find better approximations to y2. So y21, if we find y21, put k equal to 1. So y20. So y20 is obtained already in previous step by using Euler's method. So use this y20 here. So y20 is this 2.9142. So using this y20 we find y21, which is better approximation to y2, and it is found to be 2.9386. Again using the same formula we get better approximation to y2, which is y22, and here we replace y20 by y21. So in this formula we replace y20 by y21 and keep all other as they are. So we get here 2.9392 as the better approximation to y2. So next better approximation to y2 is 2.9392. Again using the same formula y23 we get better approximation to y2 as 2.9392. So here we replace y21 by y22. So y22 is here 2.9392. So we get 2.9392 as the next better approximation to y2. Since these two values are repeating, so we stop here, because if we repeat this again, we again get 2.9392. So this is now y2. So we have x2 equal to 2 and y2 equal to 2.9392. Now starting with this x2 y2, we find x3 y3, that means y at 2.25. So x2 is 2, y2 is 2.9392. So this is the initial estimation of y3 by using Euler's method. So Euler's method will give y30 as 2.8375. Again using the modified formula y3k. So again y2 is 2.9392 and all other values. So this value is again constant throughout the discussion. So we calculate it as 2.883 plus 0.125 f of 2.25 y3 k minus 1. So using various values of k again, you can find better approximations to y3. So y31 is given by putting k equal to 1 here. So y30 is we have already obtained here. So using y30 we get next better approximation to y3 as 2.8554. Again using the same formula we get next better approximation to y3 as y32. Here we replace y30 by y31. So the formula will be same except this value y30. We replace y30 by y31. So we get this 2.8562. Again using the same formula and replacing y31 by y32, we get 2.8563 as the next better approximation. So we have to repeat this up to 4 times to get these two values stable. So here we see that these two values are repeating. Therefore this is the approximation to y3. So this is the value of y3, that is y at 2.25. So now we have y at 2.25 as 2.8563. Now compare this value with the exact solution. So if we compare these values with the exact solution, we see that from exact solution, if we put x equal to 1.75 here, we get 3.0674 from this solution. And from Euler's method, we obtained this value as 3.0335, and from modified Euler's method we obtained this value as 3.0659. So you can see here the error in this value obtained from modified Euler's method is less than that obtained by using Euler's method. So this value is close to the actual value. Similarly y at 2, if we find y at 2 from this exact solution, we find that it is 2.9419. From Euler's method we find 2.8811, and from modified Euler's method we find 2.9392. So we see that this is close to exact solution. So this is better. This value is better as compared to the value obtained by Euler's method. Similarly y at 2.25 is from exact solution, it is 2.8603. From Euler's method this is 2.7762. And from modified Euler's method it is 2.8563. So these values are close. So here we find the better value of y at x equal to 2.25 using modified Euler's method as compared to Euler's method. So I hope you understood what I have told you. Thank you very much.